Hey guys, welcome back to another RASK Maths video, and in this video I'm going to be starting a new series where I'm basically going to be preparing for interviews. So the idea is I'm going to pick a question from this TBO problem solving booklet. It's quite famous, essentially it just has a bunch of questions which are interview style. I'm just going to be picking one and going over it for around 25 minutes, and then if I'm able to get the answer, I'll check it with the answer, and if I'm not able to get it within 25 minutes, then I'll look at the solution and talk about how I could have got it maybe. And yeah, just going to be trying to explain my thought process as clearly as possible. Hopefully this will be interesting, and it might be useful if you're also preparing for interviews to see perhaps how you can explain your thought process. But yeah, let's just get started. This is the first episode, so I guess I'll just start with number 1. And yeah, let's just wonder if I can just copy that and then put this in here. Right, there we go. So here's the question. Let's start a 25-minute timer to get going. All right. The question is, how many ways can you arrange each of these digits? Each of the digits 1 to 6 to create distinct 6-digit numbers. So I'm just going to write out the digits and then we can think about what it's asking. I suppose this is actually a few different parts, so let's just answer these parts separately. Okay, so let's first do A. How many ways can you arrange each of these digits to create distinct 6-digit numbers? Well, this hasn't got, these set of digits don't have any zeros, which means there's no risk of, doing 0, 1, 2, 3, 4, 5, 6, and ending up with a non-existent number. So I suppose the answer to this first part, how many ways can you arrange each of the digits 1 to 6? I suppose the answer to this is just the number of permutations of these digits, and that would be 6 factorial, because for the first slot, if we imagine we have 6 slots and we can pick each of these digits for a slot. For this first slot, we have 6 choices. Then for this second slot, we have 5 choices. For example, we could have 1, 2, 3, 4, 5, or 6 for this first slot. Then if we select one, we would have 5 remaining here, 4 for this third slot, 3 for this fourth slot, 2 for this fifth slot, and just one last digit remaining for this sixth slot. So that's going to tell us that the number of, let's call it unique permutations, because we also don't have to worry about any repeats because each of these digits is different. So we don't have to worry about, for example, if this 5 was a 4 instead, then we'd actually have to divide by the number of repeats, because let's just say we had 1, 2, 3. I'm going to say this 4 has an underline. So if we just did 6 factorial permutations, we would be counting these 2 permutations as separate ones. I've identified the different 4s with one of them underlined. These 2 would be counted separately, but we don't want to count them separately when we consider unique permutations. So if there was a repeat, we'd have to divide by 2, because for each of these permutations of these other 4 numbers, there'd be 2 with these 4 in swapped places. So we'd have to divide that out. Luckily, since all of these numbers are unique, we don't have to worry about that. So number of unique permutations is 6 factorial, and I believe that's 720. And that's equal to, I'm just going to say question A, the answer to A. How many ways you can arrange each of the digits? All right, there we go. So that was part A done. Let's move on to part B. How many of these contain the digits 1, 2, 3, 4 next to each other and in that order? Okay, again, let's just write out my digits. 1, 2, 3, 4, 4, 5, and 6. 1, 2, 3, 4, 5, 6. And it's basic. This question part B is asking how many of these permutations contain these 1, 2, 3 next to each other in that order. So one way I can see of answering this question would be to just treat this entire 1, 2, 3 as a block of numbers, and then we can consider these, the 4, 5, and 6, as just separate numbers. So now what we can do is we just have to work out the number of permutations of these items, pretending that 1, 2, 3 is one individual item. So for example, one permutation might be 1, 2, 3, 4, 5, 6. That's a valid permutation, which B wants to count. Another one could be 4, 1, 2, 3, 5, 6. Another one might be 5, 1, 2, 3, 4, 6. And this goes on and on. You can see in each of these, the 1, 2, 3 block is together in that order. These. So doing this method is going to also generate the permutations we want. So to answer question B, part B, we just have to work out the number of unique permutations of items in this set. Luckily for us, again, since none of the numbers are 0, we can just rearrange them without any hassle of worrying whether 0 will end up at the front. And we can also, none of them are the same, so we can just work out the number of permutations without having to consider duplicates. So this is a similar sort of question. Number of unique permutations. This time is only going to be equal to 4 factorial, because we're treating this block of 1, 2, 3 as a single item. So 4 factorial, so there's actually only 24 out of the 720 total permutations which contain 1, 2, 3 next to each other and in that order. So that's fine. Let's move on to part C. Probably put lines to make it clear, different parts. All right. Part C, how many arrangements does 5 occur before 1? Okay. Now, this is a bit trickier, and let's see if I can work through this. So these are our choice of numbers to select from when we're assembling our 6-digit number. And we want a number of arrangements where 5 occurs before 1. So one easy way I can see of doing this is just by symmetry. There's really nothing special about 5 and 1. And so clearly it would be the same answer if it was how many permutations does 2 occur before 3, or the other way around. And that's the important thing. Let's say number of permutations with 5 before 1 is equal to the number of permutations with 1 before 5. Because there's really nothing special about these numbers, right? They're just items in the set which we could pick to put in these spots. So if we know this is true, and we also know that every permutation either has 1 or 5 first. So there's no permutations with 1 and 5 in the same spot, because how could that happen? Then you have an empty spot somewhere. That doesn't make any sense. So in every single 6-digit number, such as 1, 4, 3, 5, 6, 2, there's always either the 1 first or the 5 first. It doesn't really matter. And so every permutation either has a 1 or 5 first. Let's say that's equivalent to no permutations with 1 and 5 in the same slot. So therefore, we know that adding these together, so number of permutations with 5 before 1 plus the number of permutations with 1 before 5 has got to be equal to the total number of permutations. And we know that this was equal to, from part A, we know this is equal to 720. These two are equal to each other. So therefore, if we just call this x, we know that 2x is equal to 720. So x, the number of permutations in which 5 occurs before 1, is equal to 1/2 times 720, or 360 times. So that was the sort of symmetrical way of seeing it. But I don't know how rigorous that is. It really relies on the fact that these are not weighted at all. There's nothing special about these. They're both equal priority, if that makes sense. But I'm going to see if I can explain it in a different way, just to make a bit more sense. So let's say we have our 6 slots where we can place our digits in over here. 1, 2, 3, 4, 5, 6. Okay. So what I'm going to do is, out of these 720 unique different numbers, okay, so let's think about this. If we place the digits, let's ignore 1 and 5 for now. So we have 4 digits, and we can place them in 6 different slots. And okay, I'm just going to create a new set of numbers. Let's say we have the digits 1, 2, sorry, not 1. Let's say the items we have available to set up our number are 2, 3, 4, 6, and I'm just going to add in an extra digit. This is like a placeholder, x. And I'll add in another x just so that we can, just so. Yeah. Okay. So now, if we consider the total permutations of these characters, number of permutations with set above, we know that there's a little formula for this, and it's essentially going to be 6 factorial over 2 factorial, because like I explained earlier, these two x's are repeats, so we want to divide out the permutations which treat x's differently. So if this was one possible arrangement, using just 6 factorial, we'd end up with 2, 3, 4, 6, x2, x1 as a separate permutation. And that is not what we want, because they're actually identical when you look at them, when you ignore the subscripts. And so for each arrangement of the 2, 3, 4, and 6, there's going to be 2 arrangements of the x1 and x2 in opposite directions. No, sorry. What's the word? How do you say it? In swapped places, I guess you could say. So yeah, we know the number of permutations with this set is going to be 6 factorial over 2 factorial, or 360. Now let's just think about what these look like. So if we have 2, 3, 4, one possible permutation might be 2, 3, 4, 6, x. We could have 2x, 4x, 6, 3, 4, 6, x, 3, x2, x, 2, 3, 4, 6. These are all possible permutations, and there's altogether 360 of these. Now, let's just say the 1 for each of these permutations, let me just check the question. Yeah, so let's just let the 5 be the first placeholder and the 1 be the second placeholder. So we'll say 5 here, and we'll put 1 here. So we don't really know what these placeholders are, but let's just define, I guess. We'll just say 5 always goes in the first placeholder, and 1 always goes in the second placeholder. So that way, we're essentially saying that the 5 is always going to be before the 1 in every single one of these permutations. And notice how there's only one way of doing that for each permutation, because there's only 2 placeholders. So there's only one way of putting a 5 before the 1. 5, 1, 1. So essentially, for each one of these unique permutations, we can add in a 5 and add in a 1 in this order, and that's going to ensure that we have 360 permutations where 5 comes before 1. So therefore, we are going to have 360 out of the possible 720, which are going to have 5 before the 1. So hopefully that makes sense. The answer to this, therefore, answer to part C is going to be 360. There were 2 explanations for that. Hopefully both of them made sense and you could understand. All right, so moving on to part 6. How many distinct 6-digit numbers are there in which all of the digits 1 to 5 appear? So that's a pretty weird question, actually, because you would think the answer is... Okay, I guess they're not talking about these arrangements anymore. They're just talking about how many distinct 6-digit numbers are there in which all of the digits 1 to 5 appear. Okay, so for this final part, maybe we can just consider how many distinct 6-digit numbers are there. So we can start with all of the digits 1 to 5, and then we can just make as many distinct 6-digit numbers as we can. Okay, so let's say these are the digits we have available. We have 1, 2, 3, 4, 5. So these are the ones which must be in the permutation. I feel like I'm using the word permutation wrong, but yeah, hopefully I'm not. Okay, so these are the numbers, the digits which must be in a permutation, and then we have some other digits remaining. So let's see, how many distinct 6-digit numbers are there? So we have these digits, and then we also have 6, 7, 8, 9, and 0 as well. And so if we were to create a 6-digit number, like so, 1, 2, 3, 1, 2, 3, 4, 5, 6. So first of all, we'd have to populate them with the 1, 2, 3, 4, 5, like so. And then we could pick any of these numbers for this remaining digit. So we could have 1, 2, 3, 4, 5, 6, 7, 8, 9, or 0 for this final digit. So clearly there are 1, 2, 3, 4, 9, there are 10 choices. I'll just put it in brackets. 10 choices for this final digit. So in this arrangement, there are 10 possibilities, but then we also have to multiply it by the number of permutations of this first bit, because, so let's say this is what's happening here. We have 1, 2, 3, 4, 5. Then our first number is going to be this. Then our second number, if we imagine a huge list of all the permutations, then this might be our first number, this might be the second number, and this would be the third number. So you can see that this is going to form all of the permutations in this format. But we also have to consider, so for each arrangement of these first 5 numbers, we have to consider each of those arrangements will have 10 different possibilities. So let me explain it like this. I'm going to use x. Let x be the placeholder. So if we start off with 1, 2, 3, 4, 5, and then x, then this could branch off as 1, 2, 3, 4, 5, 1, 1, 2, 3, 4, 5, 2, all the way down to 1, 2, 3, 4, 5, 0. So this branch, there are 10 branches for this initial permutation. And then what we could do is, if we have another branch, which is something like 2, 1, 3, 4, 5x, then this is also going to have 10 branches. Some other permutation, 3, 1, 4, 5, 2x, it's going to have 10 branches, and on and on. So clearly, if we find a permutation for this, and then we just multiply by 10, that will give us the total number of permutations which have 1, 2, 3, 4, 5 guaranteed. Just thinking about that. Yeah. So let's do that. We know if we had this as our sequence, 1, 2, 3, 4, 5, and then x for our placeholder, we know the number of unique permutations is going to be equal to 6 factorial. So therefore, you would think that the number of branches was equal to 6 factorial multiplied by 10. But there's a small problem with this. So let's just consider the permutations when x is at the start, and then we have 1, 2, 3, 4, 5, and these could be in any arrangement. So what happens when x is at the start? Well, then we can't have 0 here, can we? So the total number of arrangements here, well, we only have 1, 2, 3, 4, 5, 6, 7, 8, or 9 as options. So we only actually have 9 options now, rather than 10. So it's not as easy as just finding all of these permutations, because some of these permutations actually only have 9 options for x rather than 10. So what we need to do is find out how many of these permutations are invalid because they start with 0, and we need to subtract those. So find how many of the 6 factorial times 10 permutations start with a 0. And this isn't actually too difficult. Let's say we have a 0 here, then this would have been in the x placeholder, so the other numbers remaining would have been 1, 2, 3, 4, 5. And now the number of permutations of this is just going to give us the number at the start. So we know that these digits can be arranged in 5 factorial ways. Therefore, there are 5 factorial permutations which start with 0. Hopefully that makes sense and is correct. Which start with 0. Okay, so therefore the answer to question D, number of permutations, number of distinct 6-digit numbers for which all the digits 1 to 5 appear, is actually 6 factorial times 10 minus 5 factorial. Now I'm just trying to think about that word distinct, because if we use this method, are they all going to be distinct? Yeah, they should be actually. We need to make sure there's a way of generating every number. So for example, if we want to generate the number 1, 0, 2, 3, 4, 5, that would have come from the branch of 1x, 2, 3, 4, 5. And then this branch, this sort of root would have also contained 1, 1, 2, 3, 4, 5, 1, 2, 2, 3, 4, 5, 1, 9, 2, 3, 4, 5, all of these branches. So yeah, I think this is all of distinct 6-digit numbers in which 1 to 5 appear. So let's just lock that in as our answer. 6 factorial multiplied by 10 multiplied by minus 5 factorial. Not sure if there's any way of simplifying this, but I'm just going to leave it as that and see if that's the answer. So let's check the answers now. Put this over here. Okay. Okay. First part is simply 6 factorial, as there is no repeated element. Okay, I'm going to put this over here. Oh. Alright, so let's mark our answers. First part 6 factorial. Okay, yeah, that was pretty simple. So the unique permutation 6 factorial, able to get that. Trying not to see the answers the second bit. Yep. Second part is answered by blocking 1, 2, 3 as a single element. And third part is simply half the arrangements. Okay, so yeah, that's what we did. Block this as a single element and then find out the arrangement. So that would be 4 factorial. I'm going to say that's correct. And the third part is simply half of the arrangements. So yeah, we were able to get that as well with 360. Okay, so let's mark that correct. And then D, last part is more difficult and more care is required. Okay. The 6th digit can be any of 0 to 9, but the cases where the extra digit is 0 to 5. Ah, okay. Yeah. Okay, so I don't actually think we got this bit right, because if we were using this method, what would happen is you could have 5, 1, 2, 3, 4, 5, where x was here initially, and then we could also have another permutation where 5, 1, 2, 3, 4, 5, and x was actually here. So these would have counted as 2 separate answers, even though they actually only happen once. So, okay, so I don't actually think the answer was 6 factorial times 10 minus 5 factorial. We probably need to consider this a bit harder. Okay. Let's see if I can find the answer anywhere else. TBO problem solving booklet answers. Yeah, it's going to be hard to find the actual answer. Okay, let's see if we can figure it out for ourselves then. So, clearly, if we have 1, 2, 3, 4, 5 as our initial slots, and then we have x as our placeholder, let's just say for now, x can be 0, 6, 7, 8, or 9. Okay, so that's going to give us, using the same sort of method as above, is going to give us 6 factorial multiplied by 1, 2, 3, 4, 5. 5 is total permutations of, distinct numbers with these digits. Then we also have to subtract the ones where 0 is at the front. So that's going to be just minus 5 factorial. Okay, so those are the first cases. But now let's also consider the cases when x can be 1, 2, 3, 4, or 5. So here, we have to be a bit careful, because let's say x was 1 here. This would produce the outcome 1, 2, 3, 4, 5, 1. And let's say there was a different initial root I'll say, where x was here, and we had x as 1, this is going to produce 1, 2, 3, 4, 5, 1, which is the same thing as this. So it's not a distinct 6-digit number, but we would count them twice because x is in a different position. So how can we avoid this issue? All right. Okay, yeah, this isn't too bad. So I guess we can just consider these cases differently, separately. So let's say x can be 1. This is literally the only case we're considering. So now, in this case, our numbers available would be 1, 2, 3, 4, 5, 6. Sorry, 1, 2, 3, 4, 5, and 1. And from similar argument to the 4 I explained earlier, unique permutations of this are going to be 6 factorial over 2 factorial. That's case 1. Case 2, x can be 2. And again, this is essentially the same thing. See, there's 2 repeated numbers. So we'll say the unique permutations of this is going to be 6 factorial over 2 factorial as well. I'll just simplify that to 360. And yeah, I guess this goes on and on. So if we just add together all of these cases where x can be 1, 2, 3, 4, or 5, then we have number of unique permutations is going to be 5 for each case, multiplied by the unique permutations in each case, which is 6 factorial over 2 factorial, or 5 times 360, which is 1,800. Okay, so that's the number of unique permutations when x can be that, and when x could be 0, 6, 7, 8, or 9, we have this. So I guess we can come back and say the answer to D must be 6 factorial multiplied by 5 minus 5 factorial. And then add on these new cases plus 5 times 6 factorial over 2. And let's just simplify this down just to understand it. Plus 1,800. That's actually interesting. Why? Okay, yeah. So that's going to be 3,600 plus 1,800 minus 120, which is going to be, see if I can do this, 5520, I believe. Let's just confirm that. Sorry, no, it's a minus 120, so it's going to be 5,400 minus 120, which is 5,280. Okay, so that is my answer for part D. I think it's right now, after we've considered these cases with a bit more care. But if anyone has any ideas, let me know. I guess what I could also do is, let's just do this one more way to be even more rigorous. So let's say we know what x is, and I'm just going to say this unique permutations. So when x is 0, we can basically have any permutation of this initial sequence. Number of unique permutations of that is just 6 factorial. Sorry. We can have any permutation of this sequence except when x is here. So if we were to do this in a sort of combinatorics way, for this first number, we can have 5 different options. Second, we can also have 5 because the choices here would be 1, 2, 3, 4, 5. Choices here would be, if we chose 2, we'd have 1, 3, 4, 5, and x. And then as the remaining ones, they just decrease like this. So unique permutation is going to be 5 times 5 factorial. And then when x is 1, 2, 3, 4, or 5. Doing this case, we've already done it up here. We saw that it was just going to be equal to 6 factorial over 2 factorial, so 360. So I'll just say 6 factorial over 2 factorial. We'll put that in each of these. And then for 6, 7, 8, and 9, it's literally just 6 factorial because it's just the permutations of this with no restrictions. So each one of these is 6 factorial. So that gives us total permutations. Answer to D is going to be the sum of all of these. And let's see if I can do this. It's 5 factorial times 5 plus 1, 2, 3, 4, 5 plus 5 times 6 factorial over 2 factorial plus 4 times 6 factorial. I'm just going to type this into a calculator, although it wouldn't be too hard to evaluate this yourself. And yeah, we get 5,280. Okay, so I'm pretty sure this is the answer. Thanks for watching. Hopefully I explained my thought process well. Let me know if you were able to follow along. And yeah, thanks for watching. That was question 1 of the TBO problem solving booklet. See you guys in the next video. Bye.